this video, we'll finally dive into surface integrals. This topic is absolutely beautiful, and it's such amorphous and such abstract. It's really funny. It should also emerge from this beautifully foxy pre-drawn picture that this is really good stuff. So let's get into some context of surface integrals. So let S be a two-sided surface having projection R on the xy plane, as in the adjoining figure I've drawn here. Assuming that an equation for S is z equal to f of x and y, where f is a single valued and continuous for all x and y in R, divide R into n subregions of area delta AP, as seen here, where p is an integer from 1 to n, and erect a vertical column on each of these subregions to intersect S in an area delta SP, here. Let then phi of x, y, and z be a single valued and continuous at all points of S. Then form the sum from p equal to 1 to n of phi of delta p, eta p, sigma p times delta SP, where alpha p, eta p, sigma p is some point of delta SP. If the limit of this sum as n goes to infinity in such a way that each delta SP goes to 0 exists, the resulting limit is called the surface integral of phi of x, y, and z over S, and is designated by the double integral over R of phi of x, y, and z times the length of sec of gamma dA. The length of sec alpha is given by sec gamma. Sec gamma is equal to 1 over the length of MP dotted with K, as seen here. I should call this angle gamma P. And this is then equal to the square root of 1 plus partial derivative of z with respect to x squared plus partial derivative of z with respect to y squared. Then, assuming that z is equal to f of x and y, and that it has continuous or sectionally continuous derivatives in R, it can be written in rectangular form as the double integral, I hope you can see, the double integral over R of phi of x, y, and z times the square root of 1 plus the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared dx dy. That's just dA. In case the equation for S is given as capital F of x, y, and z, say, is equal to 0, it can also be written as the double integral over S of phi of x, y, and z times the square root of the partial derivative of x with respect to x squared plus the partial derivative of f with respect to y squared plus the partial derivative of f with respect to z squared over the length of the partial derivative of f with respect to x dx dy. It can be noted that the length of sec of gamma times dA is approximately delta SP, where gamma p is an angle between the normal line to S and the positive z axis, the limit of the sum can be written as this, if that holds. These results can be used to evaluate this equation, or if you want to substitute the s in here. In the above, we have assumed that s is such that any line parallel to the z-axis intersects s in only one point. In case s is not of this type, we can usually subdivide s into surfaces, say s1, s2, and so on and so forth, which are of this type. Then the surface integral over s is defined as the sum of the surface integrals over s1, s2, and so on and so forth. The results stated hold when s is projected onto the region R of the xy plane. In some cases, it is actually better to project s onto the yz or xz plane. For such cases, this equation can be evaluated by approximately modifying this and this equation.